Section 6.4, use inverse functions. An inverse relation interchanges the input and output values of the original relation. The graph of an inverse relation is a reflection of the graph of the original relation. The line of reflection is y equals x. To find the inverse of a relation given by an equation in x and y, switch the role of x and y, and then solve it for y. So for example, we're going to find the inverse, an equation for the inverse of the relation y equals 4x plus 2. So we're going to start by switching x and y. So we have x equals 4y plus 2. And then we're going to solve this equation for y. So we're going to subtract 2 from both sides. And then we're going to divide both sides, or every term, by 4. So we get 1/4 x minus 1/2 equals y. You could also have left it as x minus 2 over 4. This just simplifies it a little bit more. So when you have two functions, you can tell that they are inverses of each other. If we have two functions, f of x and g of x, if we do the composition of f of g of x, and we do the composition of g of f of x, both of those should equal x if the two functions are inverses of each other. And then g of x can also be written as f inverse of x. So it's f to the negative 1 of x, which is read as f inverse of x. So in our next example, we're going to verify that two functions are inverses of each other. And we're going to use this composition in order to show that they are inverses. So we have f of x is equal to 4x plus 2, and f inverse of x is equal to 1/4 x minus 1/2. So we want to verify that these are inverses of each other. So first we're going to do f of f inverse of x, and we want this to be x. So I'm going to first replace this inside function with what it is. I'm just going to substitute the 1/4 x minus 1/2 in for f inverse of x. This becomes my input variable in f of x. So instead of it being x, it's going to be 1/4 x minus 1/2. So I'm going to go to function f, and wherever I see that x, that input variable, I'm going to put in my new input variable. Now I'm going to distribute. 4 times 1/4 is just 1, so that's x. 4 times 1/2 is 2. So I have x minus 2 plus 2, which is just equal to x. So that one works. Now I'm going to do f inverse of f of x. And again, I want it to be x. So I'm going to start once again with my inside function, f of x, and I'm going to replace it by what f of x is. So f inverse of 4x plus 2. Now this becomes my input variable in f inverse of x. So I have 1/4 times my input variable, 4x plus 2, and then minus 1/2. 1/4 times 4 is just 1, so that's x. 1/4 times 2 is 1/2. So I have x plus 1/2 minus 1/2, which is just equal to x. So since they both equal x, I know that the two functions are inverses of each other. So now we're going to do a multi-step problem. And we have a small company that produces greeting cards. So the cost C in dollars of producing n greeting cards per month can be modeled by the function C equals 360 plus 0.60n. To find the inverse of the model, all we want to do is solve this for our other variable. So we're going to start by subtracting 360 from both sides. Okay, and then from here, we're going to divide both sides by 0.60 to get n by itself. And I'm going to divide each term so I can simplify it further. So I have C over 0.60 minus 600 equal to n. And the next part wants me to find the number of greeting cards produced in a month in which the company's total cost to produce the cards was $615. So I'm going to put 615 in for C. And putting that into my calculator, I get 425 cards. So sometimes you have functions, like f of x equals x squared, whose inverse is not a function. So if we replace f of x with y, we have y equals x squared, and then we switch x and y, and we go to solve this to find the inverse, we have to have that plus minus. So what that means is that when I put a value into my domain here, I'm going to get out two values in my range. So we know that that's not a function. So what we have to do on those is restrict the domain. So if we say we only want the positive values, it's a positive square root of x, and now our inverse is a function, because now for each input I only get one output. So we're going to find the inverse of a power function. We're told that f of x is equal to x squared plus 2, and x is less than or equal to 0. So we're going to find the inverse of this, and then we're going to graph the two functions. So we have y equals x squared plus 2, and then we're going to switch x and y. And then we're going to work on solving this for y. So now we have x minus 2 equals y squared, and we have to take the square root of both sides. And then we have to know which one we want. Since x was less than or equal to 0, we're actually taking the negative one. And it's a little easier to understand graphically. So I'm just going to rewrite this function underneath here. And I'm going to write it as f inverse of x. So graphically, f of x, we have a y-intercept of 2. When we put in negative 1, we are up at 3. You can also graph this on your calculator, but only look at the values of x that are less than 0. If we put in negative 2, we are up at 6. So since you have the left half here, what you want to have down here is the bottom half. And let me just write down the points here. The way you would know if it's a reflection in the line y equals x is that the x and y values switch. And graphically, inverse functions are reflections in the line y equals x. So that's what you want. So that's another way to kind of make sure that you get the right graph. So that's what the graph of the two functions would look like. This is f to the negative 1, f inverse of x. So there is a way to tell if a function, if a inverse of a function is also a function without finding the inverse. So just like we have a vertical line test for functions, we have a horizontal line test for inverses. So the horizontal line test says that if no horizontal line intersects the graph of f at more than one point, then it'll have an inverse that's a function. So, for example, for some examples. Here is a function. If I draw a horizontal line, I touch the graph more than once. So that means the inverse of this function is not a function, because the inverse will not pass the horizontal line test. Your inverse is going to end up being that way, and that will not pass the vertical line test, so it will not be a function. A graph like that is fine. It'll pass the horizontal line test, so it'll have an inverse that's a function. It's just a way to be able to tell, so you can always graph your original function, see if it passes the horizontal line test. If it does, then go about finding the inverse of it. If it doesn't, then you're already done and you can say it doesn't have an inverse. Or it doesn't have an inverse that's a function. So we're going to find the inverse of this function. So if f of x is 3x to the 5th minus 2, we're first going to determine whether the inverse of f is a function. If it is, then we're going to find the inverse. So what you can do is you can graph the function on your calculator. So you can go to y equals and put in 3x to the 5th minus 2 and graph it. And when you graph it, you should see that it will pass the horizontal line test. I know there's one point that looks kind of horizontal, but if you zoom in on it, you'll see that it really isn't. It does keep going up. You just have to kind of zoom in enough to see it. You can also kind of look at your table of values, or you could trace the graph right there and see that it is changing each time. So it does pass the horizontal line test. So we're going to find the inverse. So we're going to replace f of x with y, and then I'm going to switch x and y. And now I'm going to solve this for y. So I'm going to add 2 to both sides. And then I'm going to divide both sides by 3. And then to get rid of the 5th power, I'm going to take the 5th root of both sides. So my inverse, f to the negative 1 of x, is the 5th root of x plus 2 over 3. And then you can always do function composition.